In this video, we're going to identify what you would need to do to build one unique solution for a system of equations. With one unique solution, you'll have one and only one point at which the two lines intersect. These systems are called consistent or independent systems of equations. When we are building one of these systems of equations, are to be able to identify an example of a system that has one solution, graph the work, and also solve it by elimination if graphing is not really obvious. So let's start out by finding an example of a system of equations that are independent. So the system I'm going to give you, I'm literally making this up, but you could totally do this yourself. Basically, just find two linear equations and list them together. I'm going to go ahead and list this in standard form. The first one will be 2x plus 3y equals 6. And the second one will be x minus 2y equals 8. Notice that the signs are different on the y term, and this is important because it means that your slopes will be opposite, so you can pretty much guarantee that this will intersect in just one place. Now, to graph these, there's two different options. You could put them into slope-intercept form, or in standard form. Since we have a graph here off to the side, and standard form allows us to find the x and y intercepts very quickly, we're going to go ahead and just leave them in standard form and pick values of x and y at 0 to find the value along the y-axis intercept and along the x-axis intersection. Now we're going to let x equals 0 and substitute it into the first equation. So I'll have 2 times 0 plus 3y equals 6. So that means 3y equals 6, and y, if we divide both sides by 3, will equal 2. So when x is 0, y is 2. There's my first intersection. That's my y-intercept. Now, I'm going to also let y equal 0. This will give me my x-intercept. And then I will substitute y equals 0 into the equation. And then I will solve for x by dividing both sides by 2, which gives me x is equal to 3. So for the other intersection with the x-axis, I'll have 3, 0. And then I can draw a line through both of those points. And I'm also going to extend it out just a little bit further so that we can be sure that it will intersect the other line that we're going to graph next. Now let's go ahead and graph equation 2. When x equals 0, we get negative 2y equals 8, and that gives me y is equal to negative 4. So my first coordinate point is 0, negative 4. And then when y equals 0, we get x minus 2 times 0 equals 8. So x equals 8. So our other coordinate point is 8, 0. Now, this is going to be a little bit tricky because our graph doesn't necessarily go all the way to 8, so we're just going to have to make it one more notch right here. I think you're probably pretty confident with doing that. So now let's connect the dots. There you go. Now, if I were to just look at this graph, just visually finding the intersection, it looks like they're right there. And that point that I'm referencing is at 1, 2, 3, 4, 5, approximately 5 and approximately down 1.5. So I'm just going to label this as 5, negative 1.5. And this is a guess. This is a guess. And that is because it's approximate. Now, the elimination method will allow us to find the exact intersection of those 2 points, because this particular system that I found, that I made up, this system does not necessarily give us a nice integer answer by graphing. So elimination, it comes in really handy at this point. So I'm going to just draw a line here, and now we're going to use the elimination method to solve. So we have two equations, 2x plus 3y equals 6, and x minus 2y equals 8. At this point, we need to look at what value could I multiply both sides of an equation by to build it up so that one term will drop out if I add the two equations together. So you might want to pause the video and listen to that again because you probably have a little bit of a question. I noticed that 3 and negative 2, if I added those together, I'd get y left. I don't want anything left. So I'm going to look at the 2x and the x and notice that if I multiplied both sides of this equation by negative 2, I would have the x term drop out. So if I distribute that negative 2 into each term inside, I would get negative 2x plus 4y equals negative 16. I'm going to go ahead and rewrite the 2x plus 3y equals 6 that we didn't change anything on. And now I'm going to combine these two equations together. Notice that conveniently, the first term with the x's add to 0. 2x plus negative 2x equals 0. And I'm left with just 4y plus 3y gives me 7y. And on the right side, negative 16 plus 6 gives me negative 10. If I divide by 7 on both sides, y is equal to negative 10/7. And this is very close to the negative 1.5 that I guessed. That's good. That means that I'm probably on track to find the correct answer. Once I have this value y equals negative 10/7, substitute this value back into either equation and solve for x. It really doesn't matter which equation you substitute it back into, so I'm going to use the easier of the two, x minus 2y equals 8, and I'm going to do a substitution for the y value. In place of the y, I'm going to replace it with a negative 10/7 and then solve for x. X minus 2 times negative 10/7 equals 8. Now let's multiply these together. That will give me x plus 20/7 equals 8. And now subtract 20/7 from both sides, and I will have x is equal to 8 minus 20/7. over 7. And you can certainly put this in your calculator to get the exact value. And we get 5.14285, etc., etc. So we were extremely close when we did this guess over here when we were starting by graphing. We can see that, yes, it's very, very close to what we guessed.